then instead your dynamics is rich. In addition, if your Lagrangian doesn't depend on one coordinate, like here our Lagrangian didn't depend on x, for example, here is our Lagrangian, there is no x, there is y and theta, but there is no x. Okay? So if your Lagrangian doesn't depend on one coordinate, then we call this coordinate an ignorable coordinate. If this guy is 0, we call Qj is an ignorable coordinate. It doesn't affect the dynamics. I'm not talking about the velocity, I'm talking about the position. Because the dynamics is always affected by velocities. You have determined velocities and the kinetic energy. So this is the position. The position doesn't affect your Lagrangian. It means it doesn't affect your dynamics. We call it an ignorable coordinate. Sometimes we call it a cyclic coordinate. Like what? Like an airplane, for example, flying. The position of the airplane doesn't affect the dynamics. The airplane is here. It will have the exact same dynamics as it here, as it there, right? Doesn't affect the dynamics, the position. The same if you have a car moving on the surface. If the car is here, it has the exact same dynamics as if the car is 10 meters away, right? If you have a car moving, but suspended by a spring, then it's different. Why? Because the further you go, then the larger the force of the spring pulling you away, right? So, now, like I said, the great privilege of analytical mechanics is that you don't need to be an expert to observe these things. I'm just turning the crank and I found that my Lagrangian doesn't depend on some coordinate. The right-hand side is 0 of this equation. This means it's an ignorable coordinate. Now, look at this equation. I have d by dt partial something, d by dt for something, equals 0. This means what? D by dt for something equals 0. It means what?
Conservation.
This thing, whatever it is, right, is constant. Okay? Is conserved along the motion. This quantity, whatever it is, maybe it's very complicated quantity. R squared theta dot times cosine theta, whatever. Whatever it is, it's conserved along the motion. Its initial value equal to its final value, equal to its value at any particular moment in the excursion. Okay? What does it represent? Partial L, partial Qj dot. What does it represent? Let's have a the simplest example ever. Just 1D x position and v velocity. Your kinetic is 1/2 mv squared. Okay? And this the case will be the Lagrangian, because usually the position dependence is in the potential energy, and we from the beginning assume no dependence on the position. So this is my Lagrangian, and I'm going to do dl by partial L par partial Qj dot, which in our case is simply v, the velocity. This is what? This is mv. So indeed, in the very simple case, in the simplest case, partial L, partial velocity is
Momenta.
the momentum. Okay? In the general case, whatever it is, I don't care, this term will always represent the momentum corresponding with this degree of freedom. Okay? If it's a linear degree of freedom, it will be a translational momentum, linear momentum, mv. If it's a rotational degree of freedom theta, this guy will be an angular momentum. Okay? And you got for free that the angular momentum is conserved. Simply by just, when you do the crank, you turn your crank to solve the problem, you found that partial L, partial your coordinate is 0. This means immediately that this guy is conserved. And we're going to know now how to make use of this useful piece of information to reduce our dynamics further. Because here is an equation, right? We can use it. Any question about that? Any question? Please. Any question? Okay. When you look at this problem, our problem here. I mean, this is, to us, this is piece of cake now, right? It's two Q's subject to no constraints, and they don't have non-conservative forces. This is really easy, right? Let's do it. What is R1? This is, say, this mass 1. What's R1 for the mass on the table? Yeah, you can do R cosine theta, R sine theta in the inertial frame, or R in the ER direction. And I'm not afraid because I'm not going to differentiate twice, right? It's just the first derivative, it's easy to do it. And R2 is what? R2 is what?
L minus R.
Exactly. L minus R in what direction? If this is ER E theta, so probably E3 or N3 is upward, so this is in the negative of E3 or N3, okay? That's okay, let's do differentiate once. Once is easy, why? Because I know that this is R dot ER, and the tangential of it is always R theta dot E theta, so it's not that bad. Okay? And R2 dot, differentiate this guy please. With respect to time, L is fixed, so this is simply R dot in the E3 direction, correct? And you can see it's quite straightforward. I got the velocities, you're almost done, because your kinetic is 1/2 m this squared plus this guy squared plus this guy squared, right? So I would have 2 here. Any question? And your potential, what's your potential, please? What's the potential? What's the potential? It's mg times the vertical distance, which is L minus R, but this is below the reference, so this is negative, right? Your magic quantity, the Lagrangian, E minus V, so this is 1/2 m 2 R dot squared plus R squared theta dot squared minus minus, so this is plus mg L minus R. From this black quantity, we'll derive all the equations of motion, right? For doing anything, you can immediately realize that partial L, partial theta is what? I mean, if you start by writing down the theta equation, yeah, partial L, partial theta dot, here it is, and also partial L, partial theta, you would need to get it anyway to continue your problem, and you immediately realize that it's what?
0.
It's 0. We don't have non-conservative forces, we don't have constraints. This means that theta is ignorable coordinate. Theta doesn't affect your dynamics. The value of theta per se doesn't affect your dynamics. Theta is an ignorable coordinate. That's okay, but what does it imply?
Angular momentum.
Exactly, it implies that the corresponding momentum is conserved. What's the corresponding momentum?
Angular.
It's partial L, partial theta dot, right? This is what the Lagrangian mechanics is giving you. Simply get partial L, partial generalized velocity. Partial L, partial theta dot. This is conserved. You don't need to go and think about what is the angular momentum, and you know how maybe tricky it is. You need to get the position, the velocity, and do the cross product in Newtonian mechanics, right? Here it's just turning the crank. So the implication is that partial L, partial theta dot is conserved, a constant quantity. Partial L, partial theta dot, what's that please? This is mr squared theta dot. This quantity, whatever it is, this is conserved. This is constant along the motion. Its value, initial value, equal its value at any particular moment. Okay? Can you get this from Newtonian mechanics? Yes, of course. But you need to be really clever. Why? Here it is. Look at this. Look at this. What are the acting forces?
Gravity.
This guy, along the vertical direction, I have normal force, right? And I have gravity, and probably they balance each other because there is no motion for this guy in the vertical direction. So just forget about it. Now, for this guy, the only acting now is the tension, right? And look at the tension passes through the origin, okay? So it doesn't produce any moment about the origin. That's okay. What about this guy? This guy, I have the tension coming from here, and again it passes through the origin. So all the forces pass through the origin. So there are no moments about the origin. Summation moment about the origin is 0. It means what? It means that the angular momentum about the origin is conserved. So you can get it from Newtonian mechanics, but like I said, you need some contemplation first before you start the problem. Look at the problem by an eye of an expert to get it, right? Here, no, you don't need this much experience. You're just turning the crank and you'll find it in your way, okay? And we will know now how to exploit it. So in Newtonian mechanics, yes, you can recognize it, that's fine, but you will not have a constructive means to exploit it, to make use of this piece of information, okay? The first thing that I want to stress is that don't go back and substitute, don't eliminate theta dot from here. So I will call this constant. Since it's the angular momentum about theta, we're going to call it p theta. Okay? And we know that b theta is constant. So theta dot indeed is p theta divided by mr squared. I know that my L doesn't have theta. This is what started all this, right? My L doesn't have theta, it only has theta dot. So if I got rid of theta dot, only in terms of R, then my dynamics is reduced one-dimensional. This is great, and we're going to see why. Obviously, it's great, right? But I'm going to tell you how can we make it even better. If you can get rid of one of the degrees of freedom, that's fine. So yes, but please don't do it this way, because this is not correct. I'll tell you how to do it. How to do it is to define a new Lagrangian. Yeah, please pay attention here. So I'm saying that, yes, all this is great. And I realize that my angular momentum is conserved. So I have an additional equation. I want to make use of it. So don't do it the intuitive way. The intuitive way is that, okay, here is an equation for theta dot. Just put it there. I have my L now. That's function of R and R dot only. And live with one dimension. No, don't do it this way. This will be wrong. Okay? Here is how we do it. It's just a simple additional step. We define a new function called Lothian. R is simply your Lagrangian minus p theta times theta. And work with your Lothian as if it is your new Lagrangian. So let's do it. My Lothian is, whenever I have Lagrangian over there, so it's 1/2 m to r dot square, r square theta dot square, plus mgl minus r minus p theta theta dot. Okay? Any question about that, please? Any question? So I define the new function minus p theta theta dot, and will always be the case. If we're talking about x, then this will be px x dot. Talking about y, py y dot. It's always be like this, okay? We will generalize it later, but let's do it here for the case of theta. Now I can remove my theta here. So don't remove it before adding this term. Okay? This is the thing. So this is p theta squared over m squared r4, p theta over mr squared. You will always have this term here. They will add together. They will actually subtract from each other. Always, this will always be the case. Okay? It's kind of a check for yourself. This term will always be replicated somewhere in your terms, and they will always be subtracted. So this is as is, it's mr dot square. This term is p theta squared divided by mr squared, 1/2 minus 1. So I get minus 1/2 plus whatever you have from here, mgl minus of. This is your new Lagrangian, we just call it Ruthian. Play with it as if it's a Lagrangian function. We're going to use it to... The main thing is that it's function only of r and r dots. You reduced your dynamics by 1 degree of freedom. That's great. We don't have a holonomic constraint to do that. This was not easy to produce from the beginning. We did not have a holonomic constraint to get 1 degrees of freedom. But the analytical mechanics give you some way of doing it. First, recognize that you have an ignorable coordinate. What's the definition of an ignorable coordinate? That is, your Lagrangian doesn't depend on it. It doesn't show up in your Lagrangian. Okay? But remember, you must also have no non-conservative forces and constraints on the right-hand side of this particular thing. If this is really the case, then here is the implication, is that your momentum corresponding to this coordinate, here it's angular, is conservative. It's equal to constant. How to make use of this piece of information to reduce our dynamics further? That's perfectly fine. Subtract your Lagrangian from this term. You get a new Lagrangian, play with it. The new Lagrangian doesn't have any of the coordinates, right? Because you can remove the coordinate from the beginning. Okay? This is the correct Lagrangian. Now we're going to deal with it as just the usual Lagrangian. It's function of r and r dot only. We're going to write down an r equation only. R double dot equals, and that's it. Please, if you have any question, don't let it pass. Please. Please, any questions, please? Yes, sir.
So we have to make sure that there's no non-conservative forces before we can do that.
Oh, yeah.
Yeah, there is, but you can't.
Yeah, if you have, okay, you may have non-conservative forces in general, but they might not affect this particular coordinate.
Right.
So you need to get, is it? Yeah. You need to get the one corresponding to this little QG. So maybe there are non-conservative forces, but they are not affecting the thing.
Then you can do it.
Yeah.
Okay.
Okay, I have this Ruthian, so my R equation, what's my R equation, little r equation? It's d by dt, partial. It's supposed to be L with respect to r dot, now I'm using r, minus partial. Supposed to be L with respect to r, again I'm using the Ruthian. This is equal indeed 0 because no